Okay, so let's get started. And it's my great pleasure to introduce Bonan Zhu, who's a postdoc at UCL in the chemistry department with David Scanlon. And he's going to be leading this latest software spotlight series that we've been doing for the Hub and the TYC. And this is going to be recorded and available on the Hub website for posterity. And really, I'm very pleased that we've got someone in here who's experienced and can talk about VASP. And really, it's one that we should have started with, because VASP is by far and away the most widely used code on the Young machine, as it is also for electronic structure calculations on Archer. So it's really important that we try and educate the users to get the most out of VASP and to be aware of all of its functionality and how to use it in the most effective manner. So without me chatting anymore, making sure that we have lots of time for questions at the end and a bit more of a Q&A, let me pass over now to Bonan. And he will lead us through how he sets up and analyzes his calculations in VASP on the Young machine. So thank you very much, Bonan. Take it away.
Thank you for the introduction. It's my pleasure to sort of run this Hub Software Spotlight series for VASP. So I will just... The first part of the series would be some background and scientific motivations. I mean, if you are already very familiar with sort of plane wave DFT, this may sound a bit simple to you, but I would just kind of level the playground here, so we can have a sort of a better talk for a sort of general audience. So like George has already said, VASP is a sort of highly used code for sort of materials modeling, essentially. Here I have the data, which is not for Young, but for Archer 2. You can see it has taken a very strong lead in the sort of total time spent on Archer. The data is for January 2022, which has been a while, but like the trend is still staying till now. So what can VASP do is a sort of general purpose density functional theory code. That's how I like to describe it. It has a rich set of features. It has sort of excellent coverage of the periodic table in terms of like what elements you can choose to do your calculations. It's quite fast. It's ab initio, so it's like you don't have to consult experimental data or fits your potentials. It's written in Fortran, which is more than Fortran, but if you look at the source code, there are some kind of old-fashioned styles. It's the very good thing about it, very important for sort of materials modeling and computational perspective, is highly parallelizable. And because it's widely used, there are a lot of processing options, pre-processing and post-processing options. So just like running a bit of basics about what DFT is. So essentially, we want to solve this like Schrodinger equation, which has many terms. But if we just focus on the electronic part and kind of throw away the nuclear interactions and assume that's kind of classical, we can have this expression of the Hamiltonian. But the problem here is really the wave function, which is if you have a multi-electron system, which most materials are, is essentially a many-body wave function, which has multiple dimensions. It would be 3. For n particles, there are 3 n dimensions. So this does not sound too bad. However, if you like think about it carefully, say we want to have a wave function, we want to describe it in a real space grid, 10 by 10 by 10 is like fairly coarse. And then we need 10, because like the dimensionality here, you need an awful lot of floating point numbers, and these can easily exceed the number of like atoms in the universe. So this is not a very good idea. And because this wave function is very complex, has multiple variables, it's very difficult to sort of deal with directly. However, we're not actually interested in solving the full wave function. We just need to like do science. We need to solve the observables. And a closely related quantity to the wave function is the electron density, which only has a single variable. Well, 3, the x, y, z, or the Cartesian coordinates. So that's a much easier thing to deal with. So what DFT does is like transfer our original problem into one that solves the sort of ground state electron density. And it has been shown by this Holmberg-Kwong theorem that sort of this has a sort of unique solution for the ground state. And as such as sort of a general functional of the energy exists depends on the sort of electron density. And basically what we do is we sort of solve, we kind of change the electron density until we reach the minimum energy given the functional. And the sort of the flavor of this DFT, what we do here is called, so it's actually called Kongshan DFT, which we actually solve an auxiliary system of non-interacting atoms. So sort of to further simplify the problem. And essentially end up with this equation for the energy, which the first term is the kinetic energy. This is the sort of external potential, the Hartree energy for electron-electron interaction, the ionic interaction energy, and then this exchange correlation term, which is a function of the electron density. And essentially all the unknown things is dumped into this single term. And now we just need to seek the solution of this auxiliary system. So, so why do we want to do plane wave DFT? It's basically for this auxiliary system, we still have to have the to solve for the electron wave function, but these are single particle wave functions, and they are most efficiently represented using some kind of basis function. So one sort of natural choice for kind of solid system is the plane wave basis because of the periodic boundary, and it's especially efficient for crystalline materials, which has the periodicity. And also this is also for the computational efficiency because there is the fast Fourier transform which can efficiently transfer the plane wave basis from reciprocal space to the real space and back and forth. So here is an example. If you have a real space, you have like a plane wave, and in reciprocal space, you have this kind of, they are, so for a given sort of boundary condition, you have many plane waves. So this is like an infinite basis set, but in reality, you only choose a certain set of, a certain cutoff energy. So only the points included in this cutoff sphere are included in the basis set. And another example is if you have any function, you can sort of expand it onto this plane wave basis set. Here is an example of like this kind of square wave, and you can expand it using an increasing number of plane waves, and it gets better and better. But of course, the expanded function does not actually look at the same as the original function. This is because this square wave function is very sharp. So to solve this problem, because the in the crystal system there are nuclei and their potentials are actually quite sharp. If you think about the sort of electrostatic energies. However, in plane wave DFT, we use pseudopotential, which is essentially a sort of a soft potential that is constructed such that beyond a certain cutoff, the O electron wave functions is the same as the sort of the wave function that you solve using the sort of the pseudopotential. So beyond, essentially what I'm saying is beyond this cutoff, it's the same with the pseudopotential and with the original like atomic nuclei potential. So this is very important for having for the plane wave basis, because otherwise you will have to include awful lot many sort of plane waves for describing the wave function. And there are other schemes to sort of further improve this, and the one that in VASP is the one that VASP uses is called projector augmented wave implementation, which essentially allows to use a very relatively small cutoff energy, or in other words, a relatively small set of plane wave bases. It also has some nice properties, such as it's possible to reconstruct O electron wave function, which can be quite useful for some post-processing workflows. The other important ingredient for any DFT calculation is the actual functional we use. So there are multiple ones. These are all implemented in VASP. The simplest one is the local density approximation, which essentially just assumes the electron behaves like a free electron. This is because the electron density in solids are actually not that are relatively sort of loose. So it's like behaving quite similar to free electrons, but not always. There's also other flavors, which includes the kind of so-called semi-local generalized gradient approximation, which includes both the local density and also the gradient of the local density. There are, you can go down the gradient expansion. There's meta GGA, which includes the sort of the second derivative of the gradient. There are also hybrid functionals, which mix a bit of Hartree-Fock exchange into the functional. And the thing to keep in mind is all these different functionals, sometimes they give slightly different results. For example, for this optimization energy, they all give very different results. In some cases, they are quite close to each other, and in other cases, they are not. And the important thing is they don't always agree with the experimental value. For example, the agreement for hydrogen is quite good, a hydrogen molecule, but for oxygen, it's overbinding the oxygen molecule. They also tend to give slightly different lattice constants, but it's not a big problem. Yeah, so sometimes you have to choose the right functional. Shop around, should be avoided, but if you can justify the choices, those are still valid choices. So what we actually do, you can think about DFT as a sort of, for materials modeling, as a calculator. Your input is just the crystal structure, the sort of positions of the atoms and the lattice vectors, and some parameters, of course. Then you put everything into the calculator, it gives you a number. And the number will be the total energy of the system. Plus an awful lot of other useful properties, because once you have the total energy of the system, it's relatively easy to get the other things, for example, force and also band structures. So because, what we're looking for is actually solve the system to minimize the total energy. So the total energy is essentially the central quantity here. And very often we have to alter these coordinates of the atoms to further lower the energy. Which is called a structural relaxation, and VASP has built-in geometry optimization routines to do this, and this is like routinely done in day-to-day calculations. And such a relaxed structure is often the starting point for many sort of more detailed studies. So just to give some simple case studies about my research, well, sort of similar, kind of related to my research, is lithium-ion cathode materials. Which they have a few key properties that we're interested in experimentally and computationally. First thing, for cathode material, they must generate a sort of a sufficient voltage, otherwise it's not really a cathode. So to calculate the voltage, actually, it's quite simple. You have this equation, of course, with all the approximations taken in. So you basically need the energy of the lithiated phase, the energy of the delithiated phase, and the energy of metallic lithium, and also the number of lithium you remove from the in the delithiated phase. And there is also the Faraday constant here, but we use the atomic. If we use the unit system we have, is basically 1. So I'll give you an example of this, how we do this on Yang later. But essentially, what people can get is you can have these kind of because by calculating the energy of many different delithiation levels, you can form this convex hull. And then from the convex hull, you can extract these kind of voltage profiles, which in many cases actually agrees with the experiment very well. So the other interesting property of a cathode material is basically whether lithium can move in the material and how easy it is. So because essentially, in battery, when you charge battery, you remove the lithium from the cathode material. And when you discharge them, you put lithium back in. Of course, if the lithium cannot move, then you can't really do anything. So the sort of method we use here is often the elastic band approach, which basically involves forming a sort of so-called sort of notched elastic band between the two end states. And this allows us to obtain this transition state energy. And essentially what this band does is it follows the energy landscape, and then you can sort of get the energy of this sort of subtle point. And the key quantity here is the forces. It's both the forces and the energy. So again, this is also related to the energy, which is the central quantity in any calculation. The other very important thing is dynamical stability, because I mean you can essentially build any crystal structure you have and put it into a calculator that would give you energy and force, but whether these is really stable or not is not that obvious. So what this does is you basically do this phonon calculation by through finite displacement. So you move the structure a little bit, disperse the atoms, and then the forces will be post-processed to allow extraction of these kind of phonon dispersion. So in this example, this is a material that I searched through crystal structure prediction, and it turns out this is not the lowest energy structure, because it has imaginary frequencies and sort of a known gamma point. So what actually the lowest energy structure is like this. This is after I follow this normal mode and push the material, this allows it to go into a sort of lower energy structure. And this also requires this unit cell to be expanded as well. So typically in VASP, we use phonon pi for finite displacement phonon. So you do a bunch of single point calculations for the forces, but these calculations has to be done very accurately. The other thing we do is band structure, which is essentially, this is the reciprocal space of this unit cell. We calculate the eigenvalues at following a specific path in this reciprocal space going through the high symmetry points. This is slightly different for the total energy calculation, which is you do you sample a grid of k points in this reciprocal space and sort of essentially do an integration. But here it allows us to extract a rich set of the electronic structure information. In this particular case, it allows us to extract the sort of band gap, whether to assess whether the material is direct band gap or an indirect band gap. And also allows us to access the sort of electron mobility at the band edges. And yeah, so, and this is all quite important for identifying transparent conducting oxides. The other important thing is for kind of a more kind of material discovery focused workflow is the thermodynamic stability. Because essentially we have a calculator, it gives the energy, and the energy is quite accurate. So we can do lots of calculations and construct chemical reactions and see whether the reaction is releasing energy or not releasing energy. And this allows us to have these kind of decomposition reactions, and we can test if the energy is positive or negative. If the energy is negative, then that means this material is probably not stable. I mean, it's actually a bit more complex than that, but it allows us to obtain the stability region of a specific material in terms of the sort of chemical potentials. And based on this stability analysis, this allows the defect transition state to be calculated. And again, this is a sort of formation energy of defects. And if you look at the equation, it actually mostly involving the energies. So for this example, this is a transparent conducting oxide material. So it turns out like by doing all these calculations, we found the gallium dopant can be quite useful in like resonance doping, and turns this wide bandgap oxide into a sort of semiconducting material. So the other thing to keep in mind in DFT is the energies you get will have some systematic errors. Some of them are intrinsic to the methodology, and some of them are due to sort of approximations we have to make when we run the calculations. So in this example, if you do the formation energy of a bunch of oxide, you can see they are all shifted along this kind of ideal line. And in other cases, if you expand the set to transition metals, you can see actually transition metals are not behaving too bad. Some of them are closer to line, but they're close to line for the wrong reason, because there are error cancellations. And for transition metals, often we have to apply this GGA plus U correction. But the thing is, this is essentially introducing an extra parameter and often is fitted to the experimental data, which if you fit the U for a specific property, in this case, the formation energy, it may not be ideal for other things. So this is just something to keep in mind. And the other sort of area where a standard DIT usually is known to fail is the band gap, because so in the essentially the y-axis is its theoretical band gap and the axis is the experimental band gap. If the things is going well, they should all lie in this diagonal line, but it turns out the sort of standard DFT functionals, local density approximation and the PV, they all have a tendency to under predict the band gap, which can be a big problem for kind of studying semiconducting materials and also defects. So one way to solve this problem is to use the so-called hybrid functional, and these are very expensive compared to standard DFT calculations, but they can give very accurate band gaps and spectral properties, which are essentially for defect studies. However, they have they have worse scaling, which I mean we'll see later, actually. So it's sort of the computational cost can increase rapidly with the size of the system. And essentially the equation they use is essentially mix in a bit of Hartree-Fock exchange energy with the standard exchange energy in the local, the generalized gradient approximation. And it's controlled by various factors here. However, the good news is VASP is actually, although it is known that hybrid functionals are not so efficient when you use plane wave basis, VASP is actually very well optimized to tackle these. And massive parallel calculations can be performed. And this is what I think why VASP has a very high usage on Archer 2, because many of these kind of massive parallel calculations are for these hybrid functionals, which are intrinsically very expensive. So this is the first part. Not sure if we need to do any questions, or do we move straight into the second part? George, any?
I suggest we move
okay.
on,
yeah,
and take questions at the end.
Okay, cool. So the second part is kind of more kind of hands-on focused. So in VASP, I mean, it's a Fortran code, and the basic way for any I/O is through files. So to run any calculation, essentially all you need are 4 files: the incar file, which is for input parameters, the KPoint for specify the KPoint sampling in the reciprocal space, and also this podcar file, which is for pseudopentials. This is essentially your PAW dataset. And I mean, the first 2 files, I mean, all of them are actually just plain text. The podcar is slightly different because you have to sort of make your own podcar for a specific calculation by concatenating podcars for specific elements into a single file. So it's like essentially a sequential thing. And the postcar is also very important. Is for specifying the lattice and atomic coordinates. And so VASP actually does not know which atom is which. The only way it knows is by looking at the sort of the order that you specify them in postcar, and which has to be identical to the podcar. So when you set up a calculation, or you specify your coordinates, you can't really do something like this. You have to group them, the group elements with the same, group atoms with the same element together. Well, in theory, you could do this, but you will have to have a very long podcar, which is cadmium and telluride. Cadmium and telluride have to repeat it, and that's not very efficient. Yeah, those are just some small points that you have to do. But in reality, although it sounds pretty complex, people have developed many scripts to do this efficiently. Yeah, so some tips and some examples. So here's an example incar, and you have these sort of parameters specified with capital letters followed by a equal sign and some values afterwards. So some important thing to keep in mind is that there is no typo detection. If you make a typo, who knows what would happen? It may read the wrong. It may read the parameter into the wrong parameter. And the other very surprising thing is if you define the same tag twice, is actually the first appearance will take the precedence. So if I do I star equals 0, and then suddenly I want to change it, I want to change to I star equals to 1, I just added one line here. No, it doesn't work. Only the first one is being used, which can be quite surprising. Those are some other tips. You can quickly glance what elements are there in the podcar by just grab some keywords. And like I said, people usually use some script to construct the podcar. And here is the example of the podcar, which is you have your lattice vectors, you have some scaling factor, you have the elemental identities, which are actually just informative comments, doesn't do anything. But what actually matters is this value here. It tells VASP how many atoms to put, how many atoms are there for the first entry in the podcar file. And the podcar file is licensed, so don't share them. Otherwise, you're breaching the license agreement. So the actual running VASP is actually quite simple. You just type the command, the VASP underscore STD, which stands for the standard version for kind of multiple K points in the reciprocal space. There's also two variants, which is the NCL, stand for non-collinear magnetism. So if you want to do spin orbit coupling and non-collinear magnetism, you have to use this executable. There is also a VASP GAM version, which works for gamma only sampling. This is because when you only include the gamma point, the wave function can be represented using like real number rather than complex number. So that would make calculations faster and also reduce memory requirement. But in reality, we're going to run VASP in parallel using some kind of MPI launcher. So usually you type in an MPI launcher some parameters, then followed by the VASP STD. And VASP will print some kind of logging information to standard out. So usually people also divert the standard out to a specific file. And it's also very important to correctly load the libraries that was linked to the VASP specific VASP executable. So do not expect to simply type this command and run. Sometimes it will run, but sometimes it will suffer some numerical instabilities if the wrong libraries are loaded. So it can be quite sensitive to those settings. In terms of the output, VASP mostly write output in plain text as well. So you have multiple files as output. The main output is called outcar, which contains the sort of calculated quantity in a human readable fashion. There is also this countcar, which is basically the relaxed geometry in the same format as the postcard. There's a typo here, it should be postcard. There's also an XML file, which is machine readable, so you can use your XML parser, but it can get a bit difficult to read if your calculation is like killed or did not finish because of various reasons. There's also this charge car and wave car for charge density and wave functions. There are also other files as well, and the latest version of VASP supports HDF5 interface, so you can like use HDF5, write a HDF file archive, and then you can read it. In terms of what it's actually doing when you run a calculation is, conceptually, is actually quite simple. There's basically two loops. You have an inner loop, which is for solving the electronic structures. This is also sometimes called the SEF cycles. And there is also an outer loop, which moves the ions. So basically, the inner loop solves the electronic structure. Once you solve the structure, you get energy of forces, and then you move ions to lower the energy. Or if you're running an MD simulation, you're running an MD simulation. And it could be other things, for example, finite phonon, like finite displacement calculations, VASP for phonon frequencies, things like that. And some analysis information would be written in the end or also at the end of the electronic minimization. So another topic, very important topic for plane wave DFT is the convergence test, which is essentially for plane wave calculations. This is because the plane wave basis set need to be sort of tested, so that sort of gives so it gives like a good description of electronic structure. So basically, this involves increasing the cutoff energy and also the K-point sampling. So the typical approach is to just do a single point calculation without moving ions, and you increase the cutoff energy until the energy change is small enough. The same goes for the K-point sampling. So I mean, this may sound very kind of well, it's not complex. It's just like a bit of actual work. But actually, this is exactly what makes plane wave calculation good, because you know that when you increase the basis set, like the increase the cutoff energy and increase the K-point sampling, you're always going to increase the accuracy of the calculation. So it's essentially a well-behaving property. But I mean, for some other basis set, like the atomic orbitals, sometimes that may not be the case. Hence, it's actually quite important to converge energy and also force and stress if you are interested in those as well. And the convergence can be very problem specific. So you're not expected to like transfer one converge setting to another. So for example, the cutoff energy for oxides will be different from silicon. And also the K-point sampling for metal will be very different for the insulator. But you can use the very dense K-point for insulators that you convert. The very dense K-point converge for metals would work for insulators, but it's just like you're slightly wasting your computing resources. So here's an example. This is for lithium iron phosphate, which what I did. So in the first diagram here, the y-axis is the sort of energy per atom, and the x is the cutoff energy. So by increasing the cutoff energy, the energy per atom continues to change until but it's sort of the change is gradually decreasing. And if I plot the kind of the arrow with the sort of most converged value, I can have this sort of energy change diagram, which you can see as about sort of 450 or 500-ish, the change is less than sort of less than 10 millielectron volt per atom. So it's essentially converging, but you can see this diagram is quite, I mean, if you do the plane wave theory, then you can think, you will notice that this is actually not the right behavior, because when you increase the plane wave basis set, the energy should go down, it should not go up. This is because VASP have some sort of internal compensations to make the energy sort of well behaving. I think this is related to the PAW pseudopential. But essentially, what I'm saying is the energy will sort of decrease eventually, but it may continue to decrease. So sometimes the energy alone is not the right property to converge. And remember, like when you do calculation, actually it's the energy difference that matters, usually between two different phases. So transferability is what matters. So to have like a second opinion about what the cutoff energy we should choose, when you also usually compute the forces. So in this diagram, this is the maximum force in this structure, which you can see that it starts to converge after merely like 400 electron volt. So that's very promising. So that means like we don't have to go to 700, we start from 400, that's almost fine. But however, if you look at the stress, it actually converges slower. So in this case, it actually converges at 500. So in this case, I should choose 500 because I know the energy looks fine, the force is definitely okay, and most importantly, the stress is is converged at 500 cutoff. And the same goes for the K-point sampling. So I will compute all these properties with like increasingly dense K-point grid, but because material is essentially insulating, the bands are very flat. So for this particular material, you can go with like loose K-point sampling. So what I'm saying is this can be very problem dependent. So here is an example for geometry optimization, because essentially conceptually is very simple. You just move the atoms around to lower the energy. But there is a complication for a plane wave DFT calculation. when the cell size or shape is changed. It's because for plane wave basis set, although it's not dependent on the sort of it's not like a local basis set. It's not dependent on the position of the atoms. It is dependent on the size of the unit cell and the shape. So if you change the unit cell, for example, you start from this kind of a square unit cell in 2 dimensions. But if you expand the unit cell in the x direction here, what you're actually doing in the reciprocal space is you shrink the unit cell in the reciprocal space. And initially we have this cutoff circle, but because we change unit cell, if we keep our sampling k points, if we keep our sampling points the same, this circle is getting squashed. And of course, if we have an expansion of the real space, the reciprocal space will shrink. So that means your cutoff effective cutoff energy is also changing when you change the shape of the cell, and also this it's mostly to do with the size of the cell. So that's basically a problem, because by changing the cell, we're essentially changing the cutoff energy. So there are 2 ways to approach this. One is we can fix the basis set. We keep these points fixed, but now they're having different energies. So this means like the effective cutoff energy change. The other approach is you can reinitialize the basis set every time you change the cell. But the problem is the energy is no longer variational, because you are also changing the basis set. So VASP actually takes the first approach. So the basis set is always fixed during a single calculation, but when you restart, it will reinitialize it. So it's very important to keep in mind of this, because essentially when you move when you change the cell, when you change the lattice, you are changing the effective cutoff energy. And the other problem is the Pauli stress, which is due to the incompleteness of the plane wave basis, because essentially you need an infinite basis to fully describe the wave function, but we are only having a finite set, so there is a Pauli stress. But if you do the convergence test, that's you can show that once you use the cutoff energy, which has converged stress, then you can say the Pauli stress is almost 0. It's more important when you are forced to use a very low cutoff energy. So here is actually an example and some approach to alleviate this problem. So one approach is basically you can relax at a high cutoff energy. This reduces the Pauli stress, and also because the cutoff energy is high, and that means in the very flat part of the convergence graph, if the energy is high, if you move if the cutoff energy is high, if you change it to a different cutoff energy, the energy change of the whole system would be relatively small. So that's one valid approach to do it. So what I actually do it is I do multiple restarts. It's basically I do a geometry relaxation, and as long as I change the cell, I always do a restart and reinitialize the basis set. And then in the end, I do a final single point calculation, just to make sure that everything is consistent. I'm using the consistent cutoff energy. So here is an example of this material, which I think is also lithium ion phosphate. So as this is geometry optimization, the energy goes down as you would expect, and it flattens out. And I think what happened was it hit the number of maximum iterations, which is 60. But because the cell changed, I restarted, and immediately you see the energy is different. This is because initially I'm starting from this volume, and after 60 cycles, I'm ending up with a slightly smaller volume, which means the effective cutoff energy has changed, and then the energy, there's a sudden jump, and then carries on relaxation, the restart. So the degrees of freedom in the geometry optimization is controlled by this ISIF tag. So you can read all these on VASP Wiki, which is actually very useful and very comprehensive. So let's finally move to this very important topic of how to do calculations efficiently. So VASP is parallelized by this meshes parsing interface called MPI. Essentially what it does is you run multiple instances of VASP all actually running the same program. But at a certain point of in the program, there is a master node and also the other sort of tasks, and they communicate with each other to solve specific problems and make that sort of compute intensive part parallel and sort of accelerate the calculation. So normally you would launch the VASP calculations through MPI launcher, but on Yang, actually also the MPI launcher, you have to specify the number of processes. But on Yang, this is handled by a very useful wrapper called GE-run, which is called GE-run VASP SDD. It will run the calculation with the correct number of process, correct number of MPI tasks that you originally specified in the job script. So on other systems, other command will have to be used. So just a bit of background about in understanding parallelism, which I think is very important, is basically to realize that not all work is parallelizable. So if you have a serial execution, you do some work, you do some other work, you do some work, you do some other work, and some of the works are parallelizable. So in this example, the green ones are parallelizable, so we can divide them into multiple parts. And in a parallel execution, these parts get distributed to different workers. And but each worker still have to run the serial part. So this means that you're not getting the 100% parallel efficiency. So essentially the speed up can be written in this equation where the P is the fraction of the parallelizable work and the N is the number of workers. And the efficiency is essentially the speed up divided by N, which is in this expression. So if we plot the efficiency, sorry, this is plot the speed up with the number of tasks, which is the N for specific P value. So here P is 0.9, which means 90% of the work you do in a serial job can be fully parallelized. So in this case, immediately you will see that by increasing the number of tasks, your overall speed up will deviate from the ideal sort of diagonal line, which also means the efficiency will drop. However, if your problem is harder or your code is more efficient, 99% of the job can be parallelized now. So in here, you'll still see the speed up drop from the ideal line, but in a much slower fashion. So this means your calculation can run with a larger number of tasks while still maintaining a good good efficiency. So this is important. So the VASP is, the good news is VASP is highly parallel. By highly parallel, what I mean is parallelization can be done at multiple levels, but this is not automatic. So you have to specify it yourself. So essentially the central quantity for the plane wave DFT is the wave function, which is, you can think about as a multi-dimensional arrays. So there are actually more dimensions than I listed here. Sorry, it's like it's multi-dimensional array maybe. That's basically a high rank tensor. So basically you have these indices of indicating the K-point, the bands, and also the plane waves. So basically you can, for each level, you can distribute the workload into multiple sets of tasks. So the K-point distribution or K-point parallelization is actually the most efficient, but it can be sort of memory intensive. It's controlled by this parameter called K-par, and the band is controlled by this parameter called N-par, and G is controlled by the N-core. So we'll go into detail in the next few slides. So essentially what it does is, imagine you have a cube, you slice it into multiple planes. So the depth is the number of K-points, and each slice is a sort of matrix essentially with number of where the number of rows and columns is the number of plane wave coefficients or G vectors, and also the number of columns is the number of bands. So if I have this cube and I have 24 MPI tasks to distribute the workload to, so I can set K-par equals 2, which is basically saying I can distribute the workload for the K points into 2 groups. So each group would then contain 12 tasks, and that would be K-point group 1, which contains 2 K-point to work on the K-point group 2, which contains another K points. So I have 4 K points in total that gets fully distributed. Well, yeah. So, and if I look into each K point group, I have like 2 K points, but it doesn't matter now. So we're going to further distribute with by the bands and plan waves. So in this example, I'm using a 3-way distribution for the bands. So I divide these are 6 columns into 3 groups, each containing 2 columns, and I also divide the rows into 4 groups, each containing 3. So this is basically how the division of the workload is done. But of course, in the actual program, it might be slightly different than what I show here, but you get the idea. So the very important thing is to realize how many plan waves or how many bands you get for each group. So for example, here I divide it by I divide everything into 3 band groups. So each group contains 2 bands, and this is distributed on 12 processors. So each band group will have 4 processors. So that means so basically that means like how do I say this right? So basically you want each group, if you have too many groups, each group will get a fewer number of work. So you want to divide it in such a way that each group actually gets sufficient amount of work. So they're actually doing work rather than just trying to communicate with each other, which is lowering the parallel efficiency. So these is actually important, realizing how many things you have in each group. So the total number of tasks is basically the number of G-vector groups times the number of band groups times the number of K-point groups times the sort of number of images. This is another level of parallelization for things like notch elastic band calculations. So the rule of thumb in parallelization is, I think the first thing to realize is the optimal setting is going to be system dependent. What I mean by system is your material system, your compound, your how large supercell is, how many electrons there are, and also the hardware you have. And also, bad thing to do is try to use all levels of parallelization. And for plan with DFT, maximizing K-point parallelization, maximizing the K-par is probably most efficient if you have enough memory. And once you have the K-point fully parallelized or parallelized as much as possible, it's best to balance the G-vector band parallelism. So by basically having the sort of N-core similar to N-par. And the other thing is, it's not very good to have this N-core value to be too high, and you want them to be close to each other in the actual hardware, because they're going to have to do some intercommunication. Like essentially, it's the O2O communication. Also, like I said, it's very important to check that each group actually receives sufficient amount of work. Say if you have if you have an N-par which is too high, which means each band group will receive not many number of bands. That would make your parallelization slower. But having said all that, the only way to know for sure is to test. So to test it, you can just set this NSW equals 0, which means no ionic movement. We're just doing a single point calculation. And you can actually set the number of electronic steps to very low values, but you won't converge the electronic structure. That's already sufficient for analyze the timing. For harder problems like hybrid DFT, is actually relatively easy to parallelize efficiently simply because you have to do a lot of work, which is parallelizable. Yeah. So also one should also consider parallelizing among different calculations, because that's actually what gives you 100% like efficiency. If you, for example, if you're doing geometry relaxations for 1,000 materials, it's best to run each calculation using a small number of cores, but actually run these 1,000 relaxations in parallel as much as possible as independent jobs, rather than trying to run one calculation after another, but each calculation using a large number of cores. There are also other ways of parallelization to explore, which I won't cover. So here is an example about this kind of timing test. So the test system is this magnesium oxide, which contains 64 atoms. So this is an important thing to realize, that the timing can be quite different between the standard DFT GGA calculation using the PV functional and compared to the hybrid DFT HAC06 calculation. So in this example, actually, I changed the NCore, which actually changed the timing slightly. In this example, using NCore equals 10, i.e. we do a 10-way G-vector parallelization, no K-point distribution, because this is the gamma point only calculation. So using NCore equals 10 is actually slightly better than using NCore equals 5. And if I further increase the supercell using a larger NCore, actually, it can be better, but it may also drop slightly. But the difference is very, very small in this case. However, if I do hybrid DFT calculation, it all looks very different. In this example, I'm using still a gamma point only calculation, but with HAC06. In this example, if I'm using just 40 CPUs, using NCore 10 is most optimal. But if I increase the core counts, I may have to reconsider the choices. Also for this HA06 calculation involving 4K points. So actually, if I use a small number of CPUs, NCore equals 5 is most optimal. But if I increase the number of CPUs, like NCore equals 2 is most optimal. And in any case, you should not try to use a large NCore value. So this can be both system dependent and also material dependent. It depends on the level of theory that you use. Speaking of, the other problem is the memory issues for large scale calculations. You might run out of memory, and the way to sort of alleviate the problem is you can request more resources, or you can underpopulate them. The other newest addition for VASP on Yang is you can use the GPU nodes, which are actually quite good, but the speed up you get will be highly dependent on the problem that you're looking at. Still running the magnesium oxide example for the hybrid calculation, I get a very good speed up. So this is actually not done on Yang, but done on Marriott, which has a similar GPU. Using 4 GPUs, I have a sort of a similar timing compared to 320 CPU cores for this specific calculation involving hybrid functionals. However, if I just do a simple GGA calculation using the PV functional, using the GPUs is actually slower for this particular problem. So it's very important to benchmark your case and to decide whether using GPU is the right choice, because you can actually get slower if the problem is not the right one to do. So I just run some tests on Yang as well. The Yang is actually for the same problem using 4 GPUs is actually faster than Marriott, so that's pretty promising. So that concludes the practical part, and I'll just show some live demo about. Well, it's not really live demo. Just show you how the calculation works on Yang.
Okay, thank you, Bonan. Just before we move on, I think this is all fantastically useful. Thank you so much. I think it's really nice to actually understand the details of the parallelism here. But maybe we have a quick stop for questions. I know that some people have to leave at 1, but we should carry on because this will be recorded, and it is, as I say, very useful for the users. So there was one quick question in the chat. I don't know whether you have been using spin orbit coupling in your calculations, maybe for the phosphorus. Do you know what level spin orbit coupling is implemented, and how that is included?
To be honest, I don't know, because I haven't tried any spin orbit coupling myself, so I cannot speak of it. Okay,
fine. Well, then that's something I guess that can be left for people to find out from other ways. I had a quick question regarding the OpenMP. Is that something that you don't really use? And I get the feeling you kind of just set each core to be one MPI rank. Is there ever a case to use the OpenMP parallelism, and if so, when?
Yeah, so to be honest, I don't have experience with OpenMP and VASP, but my experience from other DFD code is basically it's if you can parallelize it over MPI, then MPI is usually better. But the OpenMP can be useful when you are underpopulating the nodes, because if you don't use OpenMP, you have like half of the cores are idling. So if you turn on OpenMP, I think the best part of it is like it's shared memory. So essentially, it's not taking actual memory, unlike running a actual MPI rank.
Sure. So if you're memory bound, use the OpenMP.
Yeah, I think it is as a way to recycle the cores. That's my kind of view. But of course, like I said, this can be highly system dependent. So in some cases, maybe this is very useful.
Great, thank you. So I just want to open it up very quickly. If there are questions from any of the people listening, you can either put it in the chat or unmute yourself. So we have one here. Which one is best? iBryon equals 1 or iBryon equals 2 in VASP for geometry optimization? I guess these are specific optimizers. I don't know.
Yeah, so I think iBryon equals 1 is something like a quasi-Newton, and iBryon equals 2 is the conjugate gradient. So my answer would be I don't know. So this again can be quite material specific. My advice, the only advice I can give is if one fails, try the other. Yeah. So
conjugate gradient is better at the beginning of the optimization, but once you get closer to the minimum, it's better to use second derivatives, in which case you switch. That would be the answer.
Yeah, but it also depends on how good the force accuracies are, things like that. So, or like energy landscape, whether it's soft or not, because one use force more than the other, I guess.
Yeah, it's a bit of a kind of art.
Yeah,
but if you don't know the final geometry, you start from some random choice. That it's better to start with the conjugate gradient. It's more efficient. And then once you feel that the system is going slower, basically geometry is changing less, then it's better for better precision to change.
Yeah, I think, it's a good. I think what I do is I usually use iBryon equals 2 for general purpose. And if I do, like, for example, phonon relaxation, like relaxing for the phonon, for the input of the phonon calculation, then because those has to have the force relaxed to a very high kind of level, then I use iBryon equals to 1.
Great, thank you for that. We have another question. What did you mean by restarting related to dealing with variable cell relaxation when performing a geometry optimization? So this is just when you said restarting. I guess what you mean is that you're reading back in the wave car, the charge car, you're restarting your calculation.
Yeah, so basically if you rerun the VASP executable, I mean, you will see it in the examples in a very short moment. But it's essentially you run the VASP program again, but you still read in the wave functions if they are, and you restart from the relaxed geometry of basically the output geometry of your relaxation.
Great. Okay. Well, we'll see that in the live demo.
Can I just clarify this? So does it mean that VASP sets the plane wave basis set only at the very beginning? So when you change the cell, the same basis set is kept all along. Therefore, when you stop and you start again, you start with a different basis set, and that's why the energy jumps.
Exactly. Yes. When you restart, it will still read the wave car, which is the wave function, but I think it will kind of interpolate it. Essentially, it's a reinitialization. So you change the basis set at the restart. Yeah.
Great. Okay. So one final question before we move on to some of the actual outputs and inputs. A question about the parallelism. Do you prefer to use K-par or use N-cores and N-par which is the most effective. So I think this relates back to your slide about the different ways of parallelizing.
So, I mean, my choice would be I would like maximize the K-par as much as possible. So prefer to use that if you have enough memory, because essentially when you do, the problem with K-par is that it does not distribute the memory. So if you imagine you have like a wave function of say 8 gigabytes, you run it with 2 MPIs, but you're using K-par equals to 2, so you distribute by K points. So each MPI process will still take 8 gigabytes of memory. But if you use N-core, each will take 4. And so the same for the N-par. So, but however, the K-point distribution is the most efficient. So like essentially you'll have you'll found that the K-par equals 2 calculation would be faster than N-core equals 2 or N-par equals 2 in this simple example. Yeah, so that's basically it. But the problem is so if you have a large supercell, you don't have many K points. So you are forced to use other level of parallelization as well. So it can be problem specific. Yeah.
Great. Okay, thanks. That's really clear. Okay, so let's just go on to a bit of the live demo then, and then we'll circle back if people have further questions afterwards. Thanks.
Okay, so I'll just have a demo. So you see my terminal. So basically, I will do a demo of like a brief, not this one. I'll give you an example calculation. So this is basically a relaxation of some kind of delithiated lithium ion phosphate structure. So if I want to look at the, so actually the structure looks like, sorry, just basically it's to give you an idea of what this is basically look like this. So this is like a lithium ion phosphate, but with lithium removed. So it's like a delithiated phase. So the input is basically the in-car. You have a bunch of in-car tags, parallelization settings, number of cores. Like because on Young, you have to use full nodes. So you either for this particular example, because it doesn't have many atoms, doesn't have many electrons. So I want to use a small number of cores if possible. But Young, you can only use 40 cores because you have to occupy the full node. So in example here, I'm actually requesting 2 nodes, so 80 cores. So in this particular example, I want an 8-way K-point distribution and N-core equals to 10. Yeah. So why I choose this? Because if I look at what actually the calculation is doing, number of bands and number of K points, I can do this. You can like check the number of K points and number of bands I have. So in this particular example, because I already know beforehand I have 24 K points, so having an 8-way distribution of K point is not a problem. And I know I have lots of bands to parallelize, also lots of plane wave coefficients. So that's basically, so what I recommend to actually do this, because I know this already. What you can do is you can run VASP for like 5 seconds and then kill it. And then it will print these kind of things, then you can reread how many K points you have and decide the best like parallelization settings. So in this particular example, so this is basically in-car, post-car is something like this, which is not very informative, but you can see the number of elements and the coordinates here. The K point is just the grid. Here I just use a 3x5x6. The important thing is if you have a supercell, then you should reduce the grid. And if you start from a supercell and you want to do like a primitive cell calculation, you should increase the grid. The key is to keep the density similar in the reciprocal space. The podcar, like I said, you can just grab some keywords because I know I'm using a PBE podcar. I can grab it and it shows me the elements. It's very important to have this matching what is there in the postcard because that's a common mistake to make. You want to change something in the postcard and then you rerun the calculation, but the postcard is still the same. So if you deleted lithium, you have to delete the part, the lithium part in the postcard as well. Yeah, so basically that's it. The actual job script on Yang, you can get all these on the excellent documentation website of UCL Research Computing. The key is to make sure you load the modules correctly, and you load the modules that the VASP code is actually compiled with. To see that, what you can do is you do module AV VASP. Oh, sorry, this is actually on my own computer. Module AV VASP here. If you do module show, say I want to show this one, maybe the VASP 6. If you do this, it will show essentially what compile libraries it requires, and also the actual path of the VASP executable. So we just go back to the same folder as before. So let's just have a second look of the submission script. So in this particular example, I want to relax the structure. So I start from a lithium ion phosphate structure relaxed. I remove lithium and I re-relax it because I want to compute the voltage. So what I did is I load the modules, the requirements of VASP. I do a module list just so I know in the standard out what module was loaded when I run the calculation. Then I do do the first then I start the relaxation. I change some tags in the in-car, run VASP. I copy the files over. So it's very important because VASP, when it runs, it will override everything it will override all the outputs in the same folder. So it's very important that you copy the files, like if you want to restart your calculation. Otherwise, you are losing the history of your relaxation. So in this example, because I know like there's gonna be some change in the variable cell, so I do a first relaxation, and then I restart it again. So I do 2 relaxations followed by a final single point calculation, something like this. For the final single point calculation, I simply change this NSW to 0 so that it will not move the ions because I know it's already relaxed. Yeah, so that's basically it. You have to, so by restart, what I meant is you have to write multiple lines that launches VASP. You can't just write a single line, run VASP, and then expect your structure is fully relaxed and energies are consistent. Especially for variable cell relaxation, if you're not changing the cell, you can just do a single calculation, and that would give you the energy that is consistent. So that's basically it. So this is this example. So in here you can see it has multiple outcar files because I wrote this script. Yeah, so that's basically it. So to actually compute voltage, because I already did other calculations of the non-relaxed material. So I have this compute voltage script, which basically is I try to grab and find the total final energy, and then I can use the BC tools, which is part of the Linux distribution to compute the voltage. So if I run this script, it will show the lithiated phase is this energy lithiated, and also the metallic lithium reference, which is another calculation. And I do this equation and I get the voltage is about 3.3 volt, which is very close to the experimental value, which is about 3.4. So that's pretty good. We can get very useful information about lithium cathode materials here. So yeah, that's so the other example I have is this convergence test. So to do convergence test, again, it's you basically in this example I only converge the cutoff energy. So I basically change cutoff energy in the in-car file, and then rerun VASP, and then copy the output to a separate file. And then I can the folder. Can have a script, so this basically brings out the energy of at each cutoff. So even if you don't plot it, you can see here is kind of energy start to converge, maybe about 450. The pressure is converging maybe after 500. The forces as well. I think these are coordinates. Now these three columns are actually the forces. So they start to converge maybe about 400, which is exactly what I showed in the plot in the slide. The other thing is the band structure calculation, which you actually you have to start from a relaxed geometry, and this is requires two calculations. So first you calculate the charge density. So again, like you have to change some settings to make sure VASP writes to the charge density, and then you switch the K point from a grid to a specific path. So this is the so-called non-SEF calculation. And in this calculation, you don't update the charge, you just calculate the eigenvalues at each K points. And then you get the final information, and it looks like this. So this is like a band structure plot. So basically how the eigenvalues change by going through the different paths. Yeah, so these are the examples.
Hey, can you say how did you make the plot? What did you use for the plot?
So yeah, so I mean, I was just about to say this. The plot I use is the tool I use is called Sumo, which is well, it's basically is developed in the group that I am currently in. So this is basically it's basically a tool to generate the K points, like the K point path by analyzing the symmetry of the material. So it basically generates this K point bands file. So these are the paths, and once you get this file, you just run the script, and then you have the VASP.xml, and you issue this command. I think it's called. Sorry, I just have to activate this. So it's called sumo band plot. Just do this. It's just Python is a bit slow, but eventually it will parse all the outputs from the VASP.run XML file and then plot the band structure. So it's basically a command line interface. Yeah, so this is the post-processing step that I meant. So VASP does not generate the plot itself, but you have to use some other tools. But the good thing is there are many tools around.
Thank you.
Yeah. So this concludes the sort of, just gonna close this. This concludes the part where I demonstrate to run calculations on Yang, but I just want to add this is not how I actually run my calculations. So the way I run my calculations is through this one, which is this is called AIDA, which is the kind of a high throughput framework, and it's a provenance management engine. Basically, it's a workflow engine. So I basically run my calculation through these kind of interface. This is like a Python notebook on my laptop, and I just have to type in all the commands. Battery is running low. Just gonna. Oh, sorry. Just oh, why there's no power? Oh, please. Okay, power is back. Yeah. So basically, I have this Python kind of interface to run. And in here, I just because it's a database, so I have some previous calculations, so I can load the lithium ion phosphate structure, and then I can just like define the calculation in such a way where I have a set of preset and also some overrides that I have. That I basically initialize everything, get a builder for the. So basically, this is like a workflow. So it has like settings. If calculation fails to converge under certain cycles, restart it until it converges, then do a final single point calculation. That's basically it. And then to actually run the calculation, just run this line, which is submit this workflow to a sort of a daemon that runs in the background. So if I do this, it will list all the running calculations that I have. Yeah, which you can see this is running. But because I have actually run this calculation yesterday, this kind of workflow engine is very useful because it can detect calculations that are duplicates. Because I ran it yesterday, today I run it, it will just give me the results straight away. So which is quite useful. So here is basically how I run the calculation. In this example, I run this, which is the lithium ion phosphate lithiated phase, and then I do delithiated phase. So basically, I make a vacancy using the input structure. Sorry, I make a structure with lithium vacancy. It's essentially just taking lithium away. If I do this, it makes a new structure, and I can sort of investigate what structure I actually make. I run this calculation again because I ran it yesterday. It's smart enough to like have everything cached. Then I can just like get the results straight away. If I run this, it probably will take a while to actually run the calculation cache. But yeah, so basically this is how I run the calculation. The good thing about using this kind of framework is your calculation is automatically handled for submission, running, and also monitoring, and also pulling the results back and parsing. So to actually compute the voltage, I have written a sort of Python function for compute the voltage, give you some warnings, but it's not much to worry about. Then I have this voltage. Here I'm just loading the computed results. So I have the voltage, which is a value about 3.27. So you will notice this is different from the one I showed because I got 3.3. So it turns out it was because the calculation I ran through this terminal was actually not converged. The geometry optimization did not converge. But if I run with this, it will warn me if it didn't converge, or it will automatically restart. Here's just some plots. So the best thing about this is because it will store both the input and output. And if you use the input, you use the output of the calculation. So the next calculation, it will automatically have everything connected. So in this example, I can, so basically this is a relaxation of the delithiated phase. I can generate this kind of prominence diagram, which you have this phase here. Maybe you can't see it clearly. So delithiate PNG. Sorry, this one is probably better. Yeah. So basically we have our relaxation workflow here, but it also records that the structure, this kind of structure with lithium vacancy, is generated by this make vacancy function, has multiple inputs, and also from this particular structure. So it also records where your input is from and where the output is going. So here, after running all this, I get my final energy, which is stored in this dictionary node, and I run this compute lithium voltage calculation and gives me a final value of the voltage. So this is actually how I run my calculations. I also have other examples like running convergence. Again, you set up your input set, some like you define number of seconds you want to run on young, number of positives to request, and just run everything, and it generates this kind of plot. In the end, you can analyze the results. The same goes for bands. So this is like, I'm just repeating the same thing, but you can have all the analysis in this Python notebook, and also some plot of the PDOS. So this is actually how I run the calculations. But anyway, back to the live demo. I just want to highlight there, like I said, there are many post-processing tools that are useful. The GNU toolkits are actually quite useful, like what I showed in the terminal. You can use grep, you can use bash script to do analysis. I think that's absolutely no problem if you choose to do that. There's also Sumo, which is for plotting band structure, which is what I showed. So PyMagin is also a very popular choice for sort of interfacing with VASP for preparing input files and parsing the output files. So AIDA VASP is what I use for running VASP calculation using the AIDA framework. So basically, the good thing is it has data provenance and it has a workflow engine. So this is my kind of my personal choice. The other useful mention is this Automate, which is I think it's specialized in this kind of high throughput calculations. So if you run some kind of relaxation for thousands of materials, this may be a very sort of good tool to do that. And there are many other softwares, and many of them are freely available. So you have to explore it a little bit. So to summarize, VASP is highly efficient, feature-rich, primary DF code for materials modeling, target system size 1 to 500, about 500 for normal DFT. Beyond that, it's still doable, but you need a very good supercomputer. It may not be the most efficient choice. It has very good coverage of the periodic table. However, for any plane wave DFT calculation, it requires convergence tests, and variable cell relaxation must be performed carefully. Otherwise, you might end up with wrong energy, which is not ideal. And finally, VASP can be run efficiently on the Hub computing cluster Yang, but users do have to set sensible parameters controlling the data distribution to achieve good parallel efficiency. And GPU accelerated VASP can be used for hard problems, but it's not the silver bullet for everything. Yeah, so that's want to acknowledge my supervisor, my group, which actually helped me learn VASP. So I only started using VASP after I joining the Scandal Materials Theory group. And also thanks for all the founding partners and all the computer resources, which is what enables me to gain all of these knowledge. Yeah, and any questions, welcome.
Thank you very much, Bonan. That was very comprehensive and really useful and targeted for the audience. So we really appreciate that. I think it is. I know we're over time, but I think it is useful to try and have a few questions if people have any. I just wanted to firstly ask: is that sumo code for the plotting of the band structures automatically and finding the right K-point path? Is that freely available, or is that an in-house code that isn't accessible?
It is freely available. I think it's open sourced by certain, but it's like freely available on GitHub. You can easily install it using Python, like pipe or conda. Yeah.
Great. Fantastic. Okay, so that can be just searched for online.
Yeah.
And I know you mentioned this right at the end, but we have just got these new GPUs in Young, and obviously GPU and hybrid architectures for the hardware is becoming more prevalent. Is your recommendation essentially, I don't want to overgeneralize, but is it essentially if you're doing hybrid DFT, then maybe look at using GPUs? Otherwise, it may not be what you're looking for. Or is that an overgeneralization?
Well, I think for hybrid sort of large cell hybrid calculations might be useful, because you have to think about all the bands and like G vectors that you're gonna distribute. I think for like small kind of, if you have a hybrid calculation for smaller cell, you're gonna get lots of K points. I think those cases are actually quite efficient for CPU compute. It's I think what struggles with this kind of large scale calculation is the kind of the band and the G vector distribution. But yeah, I'm not entirely sure. I haven't tried any small cell hybrid calculations.
Okay, but certainly in your experience, the most beneficial will be large cell hybrid calculations.
Yeah, and the hard problems are best for GPUs.
Yeah, well, that certainly constitutes, I guess, the hard problems. Excellent. Okay, so are there any other questions from those in the audience? As I said already, we are recording this, and it will be available on the Hub website. Okay, if there aren't further questions, we did have some earlier on, then I just want to thank you again, Bonan. That was really informative and really clear for how to set up VASP calculations and the things you have to think about when it comes to things like geometry optimization or parallelism and other such things. So from the MMM Hub, I just want to thank you again for that really clear seminar.
Yeah, thank you. Like I said, it's my pleasure to introduce and contribute to the MMM Hub, which I often also use a lot of computer resources from. So yeah,
well, that's good. That's what it's there for.